So how do you squeeze more insulin out of a human body? Well, it turns out you find the pancreas's built-in safety switch, and you basically just duct tape it into the RNN position.
Yeah, I mean, it definitely gets the machine running, but, when you bypass a safety mechanism like that, you entirely remove the system's ability to protect itself.
Right, exactly. And when that machine is the human body, well, overriding those internal safety switches can have some incredibly profound consequences. So welcome to today's deep dive.
Glad to be here.
Our mission for you today is all about answering that one just utterly fascinating pharmacological question right now. How we chemically force the body to produce insulin.
It's a huge topic.
It really is. We are looking at a stack of clinical and historical notes on a class of drugs called sulfonylureas. And we're going to uncover how this drug, evolved from a 1950s medical miracle to a modern-day second-line treatment. We'll get into how it actually works at a cellular level and, of course, the hidden costs of bypassing the body's natural safety systems. So, okay, let's unpack this.
And as we do, we really need to make sure we aren't just looking at what this drug does on a strict biochemical level, but, why it matters to the person actually taking it.
Oh, for sure.
Because the story of this drug, it perfectly illustrates the massive difference between simply treating a number on a lab report and treating a whole living patient.
Totally. And the origin story of this drug, it doesn't even start with diabetes at all.
No, it doesn't.
It starts with a complete medical accident in 1942.
Right.
So we are in Montpellier, France, and a French physician named Marcel Jeanbon is working in a typhoid fever ward. He's testing out a new sulfonamide antibiotic compound.
Yeah, IPTD, I think it was called.
Yep, IPTD. And he's just trying to treat these severely ill typhoid patients.
Right. His only goal at the time is fighting an infection. But the trial takes a very dark, unexpected turn.
Yeah, it does.
Several of his patients start experiencing severe, totally unexplained hypoglycemic episodes. I mean, their blood sugar is just crashing to the floor.
Just bottoming out.
Exactly. In some cases, it's so severe that the patients are going into convulsions and even slipping into comas.
Which is terrifying.
Yeah.
And Jambon didn't have the pharmacological tools to figure out why an experimental antibiotic was suddenly acting like a massive dose of insulin.
Right. It made no sense.
So he hands the mystery over to a pharmacologist colleague, Auguste Lubatiers.
And Lubatiers spends the next few years doing some just brilliant systematic detective work.
He really did.
He sets up animal models to test this IPTD compound, and he eventually proves a crucial mechanism. The drug only causes this blood sugar crash if the animal has an intact functioning pancreas.
So he essentially took animals, surgically removed their pancreases, gave them the drug,
and nothing happened.
Wow. Just nothing.
Precisely nothing. Their blood sugar stayed exactly the same.
Okay.
Which meant this chemical wasn't, acting on the peripheral tissues of the body to soak up glucose. It was directly stimulating the pancreas itself to release insulin.
That is wild. And so that detective work, which was published between, 1944 and 1946, it lays the foundation for an entirely new drug class.
Yeah.
But it took a while for this to actually reach patients, didn't it?
It did. It wasn't until 1956 that a German company, Hushist, introduced tolbutamide. This became the very first clinically successful oral sulfonylurea.
And we really need to contextualize how massive this was for you listening. Think about what it was like to be a type 2 diabetic before 1956.
It was a very different landscape.
Right. If dietary restrictions weren't working for you, your only pharmacological option was to inject yourself with insulin.
And keep in mind, injected insulin, which had been discovered back in 1921, that was originally developed for type 1 diabetes.
Oh, right, because type 1 is an autoimmune disease where the pancreas produces absolutely no insulin at all.
Exactly. So for decades, people with type 2 diabetes who, they still make insulin, but their bodies are just resistant to it.
Yeah.
They were relying on a treatment designed for a completely different disease. Tolbutamide was the very first oral pill specifically tailored for type 2 diabetes.
It's like trying to invent a new windshield wiper fluid and accidentally discovering a new type of engine fuel. Just a total left turn in pharmacology.
That's a great way to put it. And what's fascinating here is that this discovery fundamentally shifted the entire paradigm of diabetes care.
How so?
Well, instead of just replacing insulin from the outside with a needle, medicine was suddenly able to utilize the patient's remaining functioning beta cells. It was the first drug ever designed to work with the biological capacity the patient still had.
But, reading that a pill successfully lowers blood sugar is one thing. Do the clinical notes actually explain the physical mechanics of this?
Oh, they do.
Because knowing a chemical from the 1940s works doesn't really explain how it physically forces a human cell to dump insulin into the bloodstream.
They absolutely explain the mechanics, and it requires us to break down the machinery of the pancreatic beta cell itself. It's honestly a highly elegant system.
Okay, lay it on me.
So in a normal, healthy pancreas, there is a built-in safety check for releasing insulin. When you eat a meal, your blood glucose naturally rises, right?
Right.
That glucose enters the pancreatic beta cells through a transporter door called GLUT2.
Okay, so the glucose, the fuel from your meal, is now inside the cell.
Right. And once inside, that glucose is metabolized. That metabolic process raises the cell's ratio of ATP to ADP.
ATP being the energy.
Exactly. Essentially, the cell's internal energy currency goes up. Now, embedded in the outer membrane of that beta cell is a very specific, highly sensitive channel. It's called the ATP-sensitive potassium channel, or the KATP channel.
And the sources break this channel down into two main parts, right? Like a pore and a receptor.
Exactly. The pore itself, the actual doorway that lets potassium flow, is called pure 6.2. And sitting right next to it is a regulatory receptor called SU1. You can think of SUR1 as the lock on that doorway.
Okay, so the glucose acts as the fuel, it metabolizes, and the cell's energy currency, the ATP, increases. I've got that part. What actually happens to the doorway?
That rising ATP acts as the key. It causes that specific KATP channel to close.
Oh, okay.
When the door shuts, potassium suddenly stops leaking out of the cell.
Because normally it's just leaking out.
Right. And because the positively charged potassium is now trapped inside, the cell's membrane depolarizes.
Got it.
That shift in voltage is a signal. It triggers separate voltage-gated calcium channels to open. Calcium floods into the cell, and that flood of calcium is the direct, final trigger that causes vesicles full of stored insulin to fuse with the cell membrane and dump their insulin out into the bloodstream.
So it's basically a microscopic chain reaction. Potassium gets trapped, the voltage changes, and that change acts as the green light for calcium to rush in and trigger the insulin release.
It is a brilliant, self-limiting biological safety system. But here is the crucial takeaway for you to remember.
Okay.
That entire cascade is strictly glucose dependent. If there is no glucose from a meal, there is no rise in ATP. The potassium channel stays wide open, and absolutely no insulin is released. No food means no insulin.
And here's where it gets really interesting. Because the sulfonylurea drug completely bypasses that entire beautiful system.
Completely.
It doesn't wait for glucose. It actually binds directly to that SUR1 subunit, the lock on the doorway we just talked about, and it just forces the channel shut.
Yeah.
It doesn't care what the ATP energy levels are. It doesn't care if there's any glucose in the blood at all. It just hijacks the final step of the pathway and forces the door closed.
It's brute force.
Yeah. Think of the normal pancreas like a motion sensor light. It only turns on when someone walks into the room, like when glucose is actually present.
Yeah.
Taking a sulfonylurea is like taking a roll of duct tape and taping that motion sensor light switch into the on-in position permanently.
That analogy perfectly captures the mechanism. And because of how they bypass the natural triggers, sulfonylureas are classified pharmacologically as insulin secretagogues.
Secretagogues, meaning they secrete it.
Right. They secrete or squeeze insulin out of the pancreas. But it's vital to understand what they do not do. They do not fix insulin resistance at the muscle or liver level, which is what drugs like metformin try to address. And they absolutely do not work if the patient's beta cells are already dead or fully depleted.
Oh, I see. So you have to have something to squeeze.
Exactly. They require a living, functioning population of beta cells to squeeze.
But, if you duct tape a physiological switch in the on-tom position, there has to be collateral damage. If a light switch is taped on, the bulb is going to burn out faster, or you're going to waste a ton of electricity.
Precisely. And this leads us to the biggest, most glaring flaw of sulfonylureas, the severe risk of hypoglycemia.
Yeah.
If the drug forces the pancreas to pump out insulin, regardless of whether the patient has actually eaten anything, it carries a profound risk of crashing the patient's blood sugar to dangerously low levels.
And we really should emphasize what that means for a patient, because hypoglycemia isn't just, feeling a little hungry.
No, not at all.
The brain relies almost entirely on glucose to function. When it drops, the body goes into full panic mode. Profuse sweating, tremors, severe confusion, and if it drops low enough, seizures, and coma.
Which brings up a major misconception from the clinical notes. Not all sulfonylureas are created equal when it comes to this danger.
Oh, really?
Yeah, there is a massive clinical difference between the older, long-acting drugs and the newer, short-acting ones.
Okay, break that down for us.
The long-acting sulfonylureas like glyburide and chlorpropamide, they carry a vastly higher risk of causing severe prolonged hypoglycemia, particularly in the elderly or in people with impaired kidney function.
Because, I mean, if the kidneys aren't working perfectly, the drug just builds up in the system, continuously taping that switch on for hours and hours.
Exactly. It's so significant a risk that the American Geriatric Society maintains something called the Beers criteria.
The Beers criteria.
Yeah, it's a rigorously updated list of medications that are potentially inappropriate for older adults. And they specifically flag glyburide because its long half-life makes it incredibly dangerous for elderly patients.
Makes sense.
Guidelines today strongly suggest you are much better off using shorter-acting agents like glipizide or glycoside for those populations, where the drug clears the system much faster.
Got it. And while we are busting clinical misconceptions, we have to talk about the sulfa allergy myth.
Oh, yes.
I know a lot of patients, and even some practitioners, reflexively think that if a person is allergic to a sulfonamide antibiotic, like, the kind you might take for a common urinary tract infection, that they absolutely cannot take a sulfonylurea for their diabetes.
That is one of the most persistent myths in modern clinical medicine. It is true that sulfonylureas chemically contain a sulfonamide group in their molecular structure, but the actual cross-reactivity between the two drug classes is incredibly weak, like almost non-existent. Yeah. Most people who have severe allergic reactions to antibiotic sulfonamides, they're reacting to a very specific structural component called an aromatic amine.
And sulfonylureas don't have that component.
They do not have that aromatic amine structure. So reflexively, withholding a perfectly good diabetes medication just because a patient has a vaguely documented sulfa allergy on their chart, that is considered highly outdated caution today.
Huh. Good to know. Speaking of outdated, the clinical notes highlight chlorpropamide, which was one of those early first-generation drugs. And it came with some truly bizarre side effects.
It really did.
First off, it had a half-life in the body of up to 36 hours.
Which, as we just discussed with kidney function, is an absolute nightmare for dosing safely. If an elderly patient takes a daily pill with a 36-hour half-life, that drug is just stacking up in their system.
Yeah.
You end up with severe hypoglycemic episodes that can last for days, and they are notoriously resistant to just giving the patient a single dose of glucose in the ER. The drug just keeps forcing the insulin out.
And then there's the famous chlorpropamide alcohol flush.
Oh, right. It is this incredibly strange dose-independent reaction where patients experience severe uncomfortable facial flushing if they mix the drug with even a small amount of alcohol.
Wow. Just flushed red in the face.
Yeah, it's so weird and characteristic that professors still use it as a diagnostic curiosity when teaching pharmacology students. But practically speaking, because of that massive 36-hour half-life and the severe hypoglycemia risk, chlorpropamide has largely been abandoned in modern practice.
Wait, I have a question, though.
Sure.
So we have a drug that artificially forces the beta cells to pump out insulin 24 hours a day.
Yeah.
Doesn't the pancreas eventually just get exhausted? Can a biological system really sustain that kind of forced labor?
That is an excellent, highly debated question in the literature. It's often referred to as beta cell exhaustion.
Beta cell exhaustion, okay.
Yeah, and there was a major landmark study in 2006 called the 8OPT trial, a diabetes outcome progression trial.
What were they looking at?
They wanted to see what happened over time when you started newly diagnosed type 2 diabetics on monotherapy. So they compared patients taking only glyburide against patients taking only metformin or only rosiglitazone.
And what did they find?
What they found was that glyburide actually produced the fastest initial improvement in blood sugar. It dropped the lab numbers incredibly well right out of the gate.
So it looks like a massive success early on. But what happened long term?
Well, over the span of a few years, the patients on glyburide reached what is called secondary failure, significantly faster than the other two groups.
Secondary failure meaning?
Meaning the pill simply stopped working, their blood sugar crept back up, and they needed to add a second medication much sooner.
Oh, wow.
They also gained more weight and suffered far more hypoglycemic events. So it strongly feeds into the hypothesis that chronically overstimulating those beta cells by taping the switch on N might essentially wear out the very cellular machinery the drug relied on.
Man, we are starting to build a fairly concerning picture here. I mean, between the sheer exhaustion of the pancreas, the unwanted weight gain, and the severe, sometimes fatal risk of hypoglycemia,
Hmm.
you start to see why the medical community began to seriously question the long-term reality of this drug.
Absolutely.
We thought we had a miracle cure in the 50s, but as the decades went on, this sense of unease started creeping into the data, which led to some massive clinical trials that just completely shattered everything the medical establishment thought they knew about treating diabetes.
Right, and this raises an important question. Is lowering a patient's blood sugar always inherently good?
I mean, you would think so.
Because for a very long time, the medical assumption was simple and linear. Diabetes means high blood sugar. A drug lowers that blood sugar, therefore, the drug is good for the patient.
Right.
But in the 1970s, the UGDP controversy, the University Group Diabetes Program, it completely upended that assumption. This massive trial found that patients treated with tolbutamide actually had a significantly higher rate of cardiovascular death than patients who were just treated with diet alone, even though the tolbutamide was successfully lowering their glucose levels.
Oh, wow.
It caused such a panic that it resulted in the FDA slapping a severe black box warning on sulfonylureas.
Wait, I have to genuinely push back on the logic there.
Go ahead.
If a drug successfully lowers the exact bad lab number that defines the disease, the glucose, why on earth isn't that automatically considered a win for the patient? How can the primary metric of success be getting better while the patient is getting worse?
If we connect this to the bigger picture, it reveals one of the most vital philosophical lessons in all of modern pharmacology.
Which is?
Treating a lab value on a piece of paper is entirely meaningless if you do not improve the patient's actual survival and quality of life. The glucose number went down, yes. But if the patients are dying of heart attacks at a higher rate, you haven't actually helped the patient. You've just made their blood work look prettier while they die.
Man, that is a staggering realization for the medical community to face.
It really was.
And that tension played out all over again in 1998, right? With the UK PDS trial, the UK Prospective Diabetes Study.
Yes, that was a monumental 20-year trial. It did prove that intensive therapy with sulfonylureas successfully reduced microvascular complications.
Like what?
Things like retinopathy, which causes blindness, or nephropathy in the kidneys, those were reduced by about 25% compared to just dieting.
Okay, well, that's good.
It is good, but again, that microvascular benefit came at a steep macrovascular cost.
Ah.
The patients on sulfonylureas experienced significantly more weight gain and dangerous hypoglycemic episodes. And crucially, a sub-study of that exact same trial looked at overweight patients and found that those taking metformin actually had much better cardiovascular outcomes than those taking sulfonylureas.
So that was sort of the turning point.
That was the pivotal moment that helped cement metformin as the undisputed first-line therapy in almost every clinical guideline written since.
So sulfonylureas basically get pushed down the ladder. The sources describe them becoming second-class citizens in the clinical guidelines.
They did.
Especially as we transition into the modern era of medicine with newer drug classes like GLP-1 agonists and SGLT2 inhibitors taking center stage.
Exactly. And let's briefly explain why those newer drugs took over.
Yeah, let's do it.
Drugs like GLP-1 agonists basically amplify the body's natural mealtime signals, so they only work when you eat. SGLT2 inhibitors, they literally just force your kidneys to pee out excess sugar.
Oh, fascinating.
Both of these newer classes lower glucose, but they do it in a strictly glucose-dependent way. Because they aren't blindly squeezing the pancreas 204/7, they don't cause severe hypoglycemia.
That's a huge advantage.
And even more importantly, massive outcome trials have definitively shown that GLP-1s and SGLT2s actively reduce heart attacks, strokes, and cardiovascular deaths. Sulfonylureas simply haven't proven they can offer that cardiovascular protection.
So you have a drug class from the 1950s that causes weight gain, causes hypoglycemia, might exhaust the pancreas, and doesn't protect the heart. You'd think this drug would just quietly fade into the background of medical history.
You would think that.
But right when you count it out, the science delivers an absolute miracle.
Yes, it does.
In 2004, researchers made a massive discovery about a rare condition called permanent neonatal diabetes. This is a devastating condition where infants are diagnosed with diabetes before they are even 6 months old.
It's heartbreaking.
It really is. And they discovered that some of these babies had specific genetic mutations in the KCNJ11, or ABCC8 genes.
And if you recall our breakdown of the beta cell earlier, those specific genes are the exact blueprints that the body uses to build the KIR6.2 and SUR1 subunits of the KTP channel,
Right.
the exact same molecular doorway, and lock that sulfonylureas target.
Okay, so the mutation in these babies essentially breaks the lock. It leaves that potassium channel permanently wedged wide open. Because it's open, the beta cell can never depolarize, the calcium never rushes in, and the cell can never secrete insulin naturally.
Correct.
For years, the standard of care was to put these tiny babies on lifelong, multiple daily insulin injections from the moment they were diagnosed. I mean, think about the burden on those parents, constantly checking blood sugar and injecting a newborn.
It's an unimaginable stress. But then, a truly pivotal 2006 study led by researcher Ewan Pearson changed everything.
What did they do?
They realized that if they gave these infants a high enough dose of oral sulfonylureas, the drug could physically bind to that mutated SUR1 receptor and force the broken channel closed anyway.
No way.
Yes. Families who had been subjecting their tiny babies to agonizing daily injections were suddenly able to transition them entirely off insulin. They could control their baby's diabetes simply by crushing a cheap pill into their milk.
That is just incredible.
It is widely considered one of the most striking emotional success stories of translational genetics in modern diabetes care.
It really is a profound medical miracle. To go from a lifetime of needles to a simple pill, all because we finally understood the exact molecular mechanism of a drug discovered by complete accident in a French typhoid ward in 1942.
It's wild how science works sometimes.
So, what does this all mean for us today? Despite being bumped down to a second or third line treatment in the modern Western guidelines, sulfonylureas are still globally massive. Why?
Yeah.
Because they are incredibly, unbeatably cheap.
That is the stark economic reality of global medicine.
Yeah.
Sulfonylureas cost a few dollars a month. In low and middle-income countries where the prevalence of type 2 diabetes is absolutely exploding, newer drugs like GLP-1s and SGLT2s are either completely unavailable or prohibitively expensive for the average citizen. So millions and millions of people around the world still rely on sulfonylureas to survive.
Which means all the risks we talked about today are still very real daily concerns for millions of families.
They absolutely are. And if you are listening to this right now and you are caring for an older relative who is taking a drug like glyburide or glipizide, you need to be intensely aware of the hypoglycemia risk.
Definitely.
It remains a leading cause of diabetes-related emergency room visits in older adults. You have to actively watch for those warning signs. Sudden confusion, profuse sweating, shakiness, or an unexplained rapid heartbeat.
And you have to remember the fundamental mechanism of how this drug works, right?
Exactly. It tapes that safety switch into the on-end position.
Yeah.
It will relentlessly keep pushing insulin into their bloodstream, even if they've skipped breakfast and haven't eaten a single thing all day. The body's normal ability to protect itself has been overridden.
It really gives you a profound respect for the delicate, intricate balance of the human body. Which brings me to one final thought for you to take away from the deep dive.
Let's hear it.
In the source material, there is a brief mention of a totally different drug called diazoxide. It essentially does the exact opposite of a sulfonylurea. It is used clinically to treat severe hypoglycemia by forcefully propping the KATP channel open.
It's essentially the anti-sulfonylurea.
Right. It forces the safety switch to the OFF position, entirely preventing insulin from leaving the cell. So if pharmacology has given us the precise tools to artificially duct tape the body's internal safety switches, both permanently on and permanently OFF, it really makes you wonder.
Wonder what?
What other natural, self-regulating safety systems in our bodies are we currently bluntly overriding in modern medicine, entirely unaware of the long-term consequences that might not show up for decades?
That is the exact ever-present tension of pharmacology. We have the brilliance to manipulate the machinery, but we are almost always left dealing with the collateral damage.
The duct tape light switch gets the room bright, sure. But eventually, it always leaves you in the dark. Thank you so much for joining us on this deep dive. We'll see you next time.